second. So this one, we were discussing the graph of PV. I mean, this is what we did in last class, the graph of PV versus P. And I told you, okay, this P into V is a constant, which is that if all the other things are constant. Remember, whenever you are comparing variables, you're assuming that all the other variables are constant. So moles are constant, temperature is constant. We're just discussing PV versus P. And I told you that this product P into V is always a constant because pressure and volume are inversely proportional. So if pressure goes up, the volume goes down, but the product remains constant. If pressure goes down, the volume goes up, and it would still come out to be a constant. So no matter what you do, no matter how you change the pressure, you increase it, you decrease it, doesn't really matter. The product P into V would always be a constant. So that means for any pressure value, any one of them, P into V is going to be a constant, and it's going to be a straight line. That's going to be your ideal gas line. So that's your ideal gas. But I told you that a real gas is not going to be, because not all gases are exactly the same. So I explained that a real gas is not actually going to behave in a similar way. And what I meant by a real gas was, and what I mean by an ideal gas is your gas are your values that you get through these equations. Okay, remember, if you do PV is equal to nRT and you try to calculate the temperature, so it's the temperature that you calculate on your calculator. It doesn't mean that the real temperature is going to be exactly the same. So whenever you have this equation, PV is equal to nRT, whenever you use this equation to find out anything, that is just a value that you found on your calculator. It's not the real value. It's a value that you figured out using some equation. And you just assume that that equation is going to work for you. The real world is different. Okay, remember, even if you try to find moles is mass divided by MR. But in the real world, you're not going to get the same moles because the mass that you're taking, it's probably going to be impure. It's not going to be pure. Nothing is pure in the real world. So the thing is, the real world is different. So there's a world that is made or based on this equation. And then there's a world that is outside of this equation, which is your real world. And your real world behaves very slightly different than the world that your equations think that it behaves like. So the ideal gas is supposed to be a straight line, but a real gas actually takes a dip. When you go and measure the actual pressure and the actual volume, and you actually plot the product of pressure into volume, you get a dip. You don't get a straight line. And I explained why do you get a dip. The reason you got a dip was that I told you that in reality, gases attract each other. The ideal gas assumed that gases had no intermolecular forces, or it assumed that gases had negligible intermolecular forces. But in the real world, gases do have intermolecular forces, and some of them, they can at times have really, really strong intermolecular forces. So the particles slow down. If this particle is going to collide with the walls of the container, the other particles are going to pull it back, which means the particle would slow down before hitting the wall of the container. And because of that, the force of the collision would be less, and the pressure that would be exerted in reality is going to be lesser. So real gases have intermolecular forces, which is why the pressure kind of slightly decreases. So which is why the real pressure that you measure and the real volume that you measure, the product would come out to be slightly lesser compared to the one that you get from your equation. So your equation is always going to be giving you a higher value, but the real world would always be giving you a slightly lower value. Okay, so this is what we had discussed in the last class. Okay, is this clear? I mean, the recap of the last class, is this clear? Yes or no? Is this clear? Hania, Amna?
Yes, sir.
Okay. Now we're going to study the other part. The other part is what happens to the to this graph of the real gas. Okay, when you take the actual pressure and the actual volume, what happens to the graph at high pressures? Why does it shoot upwards? So what goes wrong? What goes wrong at high pressures? So I'm going to take this container, take the one that we drew, and I'm going to explain what's happening. So I'm going to explain what's happening at high pressures. So we made a mistake when we did the ideal gas equation. We constructed the ideal gas equation on a relationship. We said that pressure is inversely proportional to volume. I mean, we made that relationship, and that relationship is fine. It's fine to a certain extent, but this relationship fails under certain conditions. And that condition is, so the relationship works perfectly fine. You increase pressure, I start. एक second. So I start compressing from the top. I start applying pressure. I start increasing pressure. The gas would exactly behave according to this equation. So the gas would exactly behave according to this equation, and it would start compressing. The volume will decrease. So that's fine, increase pressure. So the pressure goes up, the volume decreases. So that means the product should remain a constant. I mean, you should get a constant straight line. But something happens. This relationship, it does not, I mean, this relationship does not work at high pressures. It does not work at high pressures. Why does it not work at high pressures? Because the equation is saying, I mean, what is the equation saying? The equation is saying you have a very high, let's say you have, hypothetically speaking, you have a very high pressure. So it states that the volume must go to 0. So you keep on compressing a gas, the volume, according to this equation, would continue to decrease. So let's say I compress it a bit more, and the particles would get closer to each other. Okay, I actually have very few particles here. So I compress it a bit more. I increase the pressure. I compress it a bit more. The volume decreases. So far, it's working. But it's not going to work beyond this point. Once all the gaps are gone, the gas eventually becomes incompressible. You keep on increasing pressure, it would reach a point that it would not compress. As long as there are gaps in the spaces around between the molecules, the gas will compress. But it's not going to compress beyond a certain point. So at very, very high pressures, ठीक है, इसको थोड़ा सा और compress कर देते हैं. Now the volume is stuck. You can't decrease the volume. So you can't decrease the volume further. So beyond a certain point, the gas becomes incompressible. So the volume does not actually go to 0, which the equation is stating. The volume actually becomes constant. So this happens to every gas. Pressure is inversely proportional to volume, but to a certain extent.
So could you please explain that again?
Okay, I'm going to explain that again. Just one second. See, Hania, I mean, what does the equation state? What does this equation state? Okay, you increase pressure, the volume must go to, you keep on increasing pressure, the volume should go to 0, right? Hania, is that clear?
Yes, sir.
Achha, but the problem is, I mean, that is for an ideal gas. It's the model of the gas that we created. You keep on increasing pressure, the volume must go to 0. But the thing is, the gas would become incompressible at a certain point. Do you get my point? I mean, can you compress this gas further? I mean, you can't. I mean, because there are no more spaces left. I mean, you could compress this gas. I mean, the gas was behaving our model, our relationship. It was behaving that relationship as long as the particles were really far apart, right? But beyond a certain point, it's not going to compress. Hani, is this point clear?
Yes, sir.
So the point was, you increase pressure, the volume goes down, right? But up to a certain point. So at very high pressures, the relationship fails. You increase pressure, but the volume stays the same. It just becomes constant at very, very high pressure, and it does not change. It becomes constant. So I keep on increasing. So I'm just going to show you once more. You're continuously compressing it, you're increasing pressure, but at a certain point, the gas becomes incompressible, and the volume, which according to the equation should go to 0, it's not going to 0. It actually becomes constant. इसके ऊपर और pressure लगाते जाओ, ठीक है? No matter how much pressure you put on this, it's not going to compress further. The volume is not going to go to, it's not going to go to 0. So this is what happens. Is this clear to everyone else? Why this relationship fails? Yes or no? Is this clear? Mahat, Sidra, is this clear? Izan, is this clear? Amna?
Yes.
Yes, sir.
Achha, so the point is that your relationship was for a hypothetical ideal gas. It's not going to work for a real gas at a certain point. It's going to work up to a certain point, but beyond a very high pressure, it's not going to work. So that means at high pressures, let's go back to our graph. At high pressures, why is the graph going up? You're increasing pressure constantly, and the volume is now stuck. It's constant. It's not changing. It's not compressing. Previously, what was happening? Pehle ho raha tha ki you increase pressure, the volume goes down, right? But now at very high pressures, the volume is now stuck. So if you keep on increasing pressure, the product P into V would continuously increase because you're increasing pressure and the volume is now constant. You're stuck with the volume. So therefore, it just continuously increases. Okay, is this point clear now to everyone? Yes or no? Is this clear?
Yes. Yes.
So I'll just sum this up again. Two things, because you'll be asked about this graph. Okay, this is kind of an important graph. So remember, you plotting PV always going to give you a constant for an ideal gas. Okay, assuming that the relationship is followed exactly to the point. Pressure increases, volume decreases, pressure decreases, volume increases, always gives you a constant. So no matter what pressure you're at, the ideal gas line would be a straight line. It would always give you the same value. It's going to be a constant, no matter what the pressure is. But a real gas kind of take this shape. What happens? What goes wrong at low pressures? At low pressures, we had assumed that gases don't have intermolecular forces, or they were negligible. But a real gas is going to have intermolecular forces. They're going to attract each other. The particles that are going to hit the walls of the container are going to slow down because of the attraction of the other molecules. They're going to slow down, which is why the pressure in reality that's going to be exerted is going to be lesser than the one that's you're getting from the equation. So So real pressure is going to come out to be lesser. So the product P into V would actually be a lesser value compared to the one that you're getting from the equation. Okay, reality mein jaake you measure the pressure gauge, you measure the volume, you get a smaller value. Izhan, remember, ideal gas, ideal gas is, it's not an actual gas. Remember, we made this relationship, we figured this out. Okay, we said that for gases, pressure is inversely proportional to volume, right? But the thing is, this relationship or any relationship that you think in the real world, okay, any XYZ, you make up an equation. That equation works under certain conditions. It's not going to work always. So when we talk about an ideal gas, I'm talking about the values that I'm getting from this equation. So this equation is actually going to fail at high pressures. This equation states you continuously increase pressure, the volume must decrease to, it should decrease to zero. So this equation is for an ideal gas. But this equation doesn't really work in reality. It's not going to work. It's going to work most of the time, but it's not going to work at very, very high pressures. Okay? Is this point clear? And I'm just going to stress the point. Okay, whenever you refer to ideal gas, I'm basically referring to the relationships that you had linked up, these relationships. Any equation has its limitations. Remember that. In the real world, any equation has its limitations for a number of reasons. Okay? Like if you're doing chemistry, what is moles? Moles is mass divided by MR, right? But the problem is, this would work if you have the mass of something that is 100% pure. In the real world, nothing is 100% pure. So the thing is, all these relationships, they work under certain criteria, under certain conditions. They're not going to work, or they're not going to work 100%. They're not going to give you 100% true values. The values would be good enough to give you an idea, but not 100% correct. So hopefully this graph is correct. So the next thing that we're going to talk about is non-ideal gas. Okay, we're going to talk about non-ideal gas now. And I'm going to focus on this graph. Remember one thing, and that is the bigger the dip, the more non-ideal, the bigger the deviation from the ideal gas line. You plot a graph for a real gas, this one is going to be even more non-ideal. This one is less non-ideal. What we refer to as non-ideal is the deviation that you get from this equation, the values that you're getting from this equation. How much are those values deviating from the actual values that you should have gotten from the equation? You should have gotten a straight line, but you're getting all these different curves. The bigger the deviation, the more non-ideal is the gas. So we're going to talk about the fact. What?
Sir, I have a question.
Yes.
What do you mean by when you say that it's an ideal gas or a non-ideal gas?
Ideal is, I'll state this again. Ideal is anything, we make this equation, okay? I'll just go over this. So we figure this out that pressure is inversely proportional to volume, right? We apply this to gases, right? And
yes,
based on this, we made the whole relationship and we created this equation that pressure is, we introduced a gas constant and we made up this equation, right? You clear?
Yes, sir.
So now the thing is, this equation is just an ideal equation. You just made this up. Okay? It's an equation which you use to measure the pressure. Not to measure the pressure, you actually calculate the pressure on your calculator. Okay? So you do some calculation, you do some math. So any value that you obtain, from this equation, that's applying to an ideal gas. I mean, there is in reality no such thing as an ideal gas. Anything hypothetically that follows exactly, let's say I do some math on my calculator and I get a temperature of 303 kelvins. Like I've been given some pressure values, I've been given some volume values, I've given some moles, and I put them in the equation, and on my calculator, I get a particular value for temperature. Do you think in reality, a gas under those pressures and volumes and those moles would give you exactly the same value like the one that you're getting on your calculator? I mean, this is the value that you're getting on your calculator. This whole thing is something that you've made that you use to estimate values, right? The real value might be slightly different. So if you go and measure the actual temperature of a gas, it might come out to be 310. Or maybe slightly, it might slightly deviate. It might come out to be 317. So do you get the point? There's a world that is made up of equations and there's a world that is the real world. Do you get this point?
जी sir, मतलब you're saying कि ideal gas is the gas that has nothing like different, जिसकी वजह से that falls into the
हाँ.
equation that we made.
So but the ideal gas is something that follows exactly this relationship. ठीक है? And this relationship is that you keep on increasing pressure, the volume must go to zero, right? So I mean, the relationship states that. So most gases, most real gases would follow that relationship, but to a certain extent. At a certain point, they would just become incompressible. Because एक point के बाद you can't keep pressing it down. It's not going to go to zero. Do you get my point? Because वो particles stuck होंगे बीच में. You can't make it go to zero. Is that point clear?
Yes sir, thank you.
ठीक है. So again, hopefully this point is clear. Okay, whenever I refer to something as an ideal gas, it's an imaginary gas that follows this equation exactly, which is basically no gas is going to follow that equation exactly. ठीक है? So it's just a made up gas that's going to follow this exactly. कि आपको अपने moles calculate किए, उसके moles exactly असल में भी वही होंगे. That is not going to happen. ठीक है? So there is going to be deviations. Now let's talk about, when I talk about non-ideal, I'm basically talking about the actual gases deviating from this equation. Okay, I put in the values, I try to measure the volume, I get a value on the calculator, asal mein jaake dekha, so I'm getting a different volume. So that means my gas is deviating from this equation. So anything that deviates from this equation is a non-ideal gas. So the question is, how do you figure out, or how do you figure out which one is a non-ideal gas? Now to figure out non-ideal gases, non-ideal gases have everything to do with intermolecular forces. You've got more intermolecular forces. So if you have more intermolecular forces, that means it's more non-ideal. It's going to deviate more. So there's going to be more deviation. It's not going to follow the PV0 nRT exactly. So it's going to have more deviation. So this is the point where we're going to start discussing. We're going to start discussing intermolecular forces now. And we're going to talk about simple covalent molecules. Okay, so our ideal gas chapter is pretty much kind of over. Okay, we're going to start discussing intermolecular forces now. Okay, if a molecule has more intermolecular forces, it's going to be non-ideal. So we're going to start focusing on these intermolecular forces. And there are three of them. The first thing is, intermolecular forces always exist in simple covalent molecules. Most of the gases that you have, I mean, simple covalent molecules That's a simple covalent molecules. They have intermolecular forces. For example, if you have a hydrogen molecule, you got another hydrogen molecule, and you have a third hydrogen molecule. These molecules are all going to have, I mean, they're flying around, they're gases. So they're all randomly flying around. And there would be some weak attractive force between these particles. So we're going to talk about these intermolecular forces, and there are three types of intermolecular forces. The first one is referred to as permanent dipoles. So you've got three types of intermolecular forces. So that's the first one, permanent dipoles. Then you have a second type of intermolecular force, and that is known as hydrogen bonds. And the third one is van der Waals forces. Okay, so you got permanent dipoles, you got hydrogen bonds, and you got van der Waals forces. Van der Waals forces have lots of other names as well. They're known as London dispersion forces or London forces. They're also known as instantaneous dipole induced dipoles. Induced dipoles. That's just a second. Just 1 second. So we're done with the ideal gases. The next is everything non-ideal depends on intermolecular forces. We're going to study intermolecular forces in a lot more detail, specifically these three forces, permanent dipoles, and remember all of them are considered to be weak forces. They're not very strong. All of them are relatively weak forces. So let's talk about the first one, permanent dipoles. What's a permanent dipole? That's the question. So we're going to start with the first one. So a permanent dipole is that if you have a periodic table, there's a thing called electronegativity, and there's a difference in electronegativity between atoms. Now, electronegativity is electronegativity is that it increases to the right and to the top. That is what electronegativity is. It means it's the tendency for an atom to attract a shared pair of electrons, or simply of an atom to gain electrons. Okay, that's what electronegativity is. Now, based on your knowledge, you know that on one side you have metals which always like to lose electrons. So the elements that are on the complete opposite side, they always tend to lose electrons. they don't really attract electrons very strongly. And the atoms that are in this corner, they really like to gain electrons. So the first question is, why do atoms on the extreme right, they like to gain electrons? That's the first question. Why do they like to gain electrons? And the question and the answer to that is, when you move to the right, you have more and more protons. An atom has more protons. For example, if you have Na over here, it has 11 protons, and you have Cl on the extreme other end, and that Cl has 17 protons. So one of the factors that when you move to the right, the atom, the nucleus of the atom has more protons, which is why there's a greater attraction for electrons. Like if I draw the sodium atom and the Cl atom, then it's fairly obvious that sodium has just 11 protons. So it's not going to be attracting its electrons that strongly. So this is 2, 8, and 1. So remember, the nucleus has just 11 protons. While chlorine on the other side, its nucleus has its nucleus has 17 protons. And 17 electrons as well. But because of the 17 protons, because of the greater charge, there's a much stronger attraction for the electrons. The nucleus is a lot more positively charged. So the electrons of sodium, this one over here specifically, gets pulled towards chlorine. So the idea is that the periodic table is full of atoms. The atoms on the right side are the ones that really like to gain electrons. Okay, is this point clear?
Yes.
Similarly, the atoms that are on the top, they also really like to gain electrons. And the reason for that is they're smaller in size. So you've got fluorine over here. So you've got chlorine over here. So, but at the same time, if fluorine is right on top of it in the periodic table, so if fluorine is right on top, and let's say this is fluorine with 9 protons. So remember this, smaller atoms, they have a stronger attraction for electrons. And the reason for that is that smaller atoms, their nucleuses are less shielded. So if there's an electron over here, the electron is going to be very strongly attracted to the nucleus of that atom. Bigger atoms, they tend to have too many electrons already. So if there's an electron around, I mean, it cannot even see the nucleus. There are too many electrons around it. So smaller atoms are less shielded. And have, because of the smaller size and because of the more exposed nucleus, the smaller atoms are less shielded and have stronger attraction for so they're going to have a stronger attraction for electrons. TK, is this point clear? You clear it? Yes or no?
Yes.
So one thing, the first thing, before we move on to permanent dipoles. Remember, not all atoms attract electrons equally. Some atoms electrons more compared to the other ones. The ones that are in this corner are very electronegative. They really like to gain electrons. You move further away, they don't really like to gain electrons that much. So now the other thing is, you've got all these molecules. So if a molecule has a difference in electronegativity, so for example, I have an HCl molecule. So if I have an HCl molecule, then we know that Cl is very electronegative. We know that Cl is right in this corner. Cl is very electronegative. That means that the shared electrons in this particular bond are slightly closer to Cl, which gives Cl a very slight negative charge and the H gets a very slight positive charge. So that's a polar molecule. That's known as a permanent dipole. So what's a permanent dipole? A permanent dipole is when you have an unequal distribution of electrons in a bond. And because of that, it results in slight positive and negative charges on the atoms. So that's known as a permanent dipole. A dipole means two poles. It literally means two poles. One is the slight positive side. The other one is the slight negative side. So you got Cl over here, which is more electronegative. Which is more electronegative. So Cl is going to pull the electrons towards itself. So that is what we refer to as permanent dipoles. So permanent dipoles are formed permanent dipoles are formed when there's a difference in electronegativity. So you need a difference in electronegativity between the atoms. If there is no difference in electronegativity, the electrons are not going to be unequally distributed. In this case, Cl is more electronegative, so the electrons get pulled slightly closer to Cl. Is this point clear to everyone? Hanya, is this clear? Zahan? Mahad, is this clear?
So is the states of matter chapter closed?
Yes. Okay, that just had PV0 energy. We will do intermolecular forces and then we'll do equilibria. Okay. So this is permanent dipoles, right? And how do permanent dipoles attract each other? Permanent dipoles attract each other because the other molecule of HCl is also going to have a permanent dipole. This other HCl molecule, the H is going to be slight positive and the Cl is going to be slight negative, and they will be attracting. So they'll be attracting each other. And that is known as a permanent dipole interaction. You got another HCl molecule, and that's your intermolecular force. Why is one HCl attracting the other HCl? HCl is a gas, remember that. Because the negative part of one molecule attracts the positive part of the other molecule, and it just continues. So which is why when we were talking about gases and ideal gases, we talked about molecules in reality attracting each other, slowing each other down. So real gases have intermolecular forces, and that is the first one, which is a permanent dipole. Okay. So just remember, we just discussed this one point, that is that you have the periodic table. I just go through this. Elements that are right in this corner are more electronegative. They like to really gain electrons. So when you have a molecule the electrons in a molecule, in a covalent molecule, are not shared equally. There's an unequal distribution, especially when there's a difference in electronegativity and the electrons are pulled closer to one of the atoms. So which is why you have a permanent dipole. And if a molecule has a permanent dipole, all of them will have a permanent dipole. They'll have positive and negative sides, and they're going to attract each other with some minor force of attraction. Okay? So let's continue this in tomorrow now. Okay? We'll discuss more about permanent dipoles in the next class. Okay? Okay, everyone.
Allah Hafiz.
Take care. Allah Hafiz.
Allah Hafiz, sir.
Assalamu alaikum, sir.
Walaikum salam.
Sorry, sir, to interrupt. Sir, I'm a new student. मुझे actually ना अभी मैंने join किया, so I don't know how it works with you. हमारे school में तो ऐसे था कि we complete a chapter and then we move on to the topical with read and write, for example. So how is it by you? Do we have to complete the topic and then move to the topical, or you give your questions by own?
नहीं, ये टॉपिकल हम कर रहे थे एक्चुअली. हम बताओ क्या कर रहे थे कि एक सेकंड, ये टॉपिकल है. ठीक है, सेंड द आइडल गैस टॉपिकल. ठीक है, the reason we can't do the idle gas topical completely, we did some questions. ठीक है, this one, so I'll share it with you. We did some questions, लेकिन the rest of the questions were about intermolecular forces. ठीक है, so we started with intermolecular forces now. Clear है? मतलब टॉपिकल हम करेंगे. ठीक है,
Okay, so sir, ये आप ही की topical होगी कि is it a book?
ये PDFs है यहाँ पे ना. ठीक है, टॉपिक वाइज, बल्कि सब टॉपिक वाइज है. ठीक है, फॉर एग्जांपल if you look at कोई भी उठा लेते हैं. जस्ट अ सेकंड, मैं यहाँ पे तो काफी ज्यादा है. जस्ट वन सेकंड, एक सेकंड, लेट मी. अच्छा, ये देख लेते हैं. तो टॉपिकल भी है प्लस सब टॉपिक वाइज है. ठीक है, you have if you go over here, जिसमें कहाँ गया अभी ये जैसा मोल्स के क्वेश्चंस डिवाइडेड बाय, अगर बैलेंसिंग के क्वेश्चंस के तो ऑल डिवाइडेड कंबशन एनालिसिस है, so all of them are just combustion analysis, hydrocarbons burning. ठीक है, उनके सारे क्वेश्चंस. तो वो वर्कशीट हम करेंगे. We did the ideal gas worksheet, we did the questions, especially just left the intermolecular forces part. ठीक है, तो वो हम इसके बाद कर लेंगे. Intermolecular forces, then we'll do past papers on intermolecular forces. ठीक है,
Okay, sir, thank you.
चले. Okay, take care. Allah Hafiz.